Hello everyone, in this video I am going to discuss about graph representation. And we can do this by using adjacency list, an adjacency matrix, and an incidence matrix. So adjacency list is one of the simplest ways on how we can represent graphs. So this list can be used to represent a graph with no multiple edges. So take note of that. So that means that we can only do this by having a simple graph without multiple edges. So, and we can do that by specifying the vertices that are adjacent to each vertex of the graph. So an example here is we have 5 vertices, A, B, C, D, and E, and we simply have to list down the adjacent vertices to a one vertex. Okay, so let's start with A. So A is adjacent to B and D. So as we mentioned here, we only have to specify the vertices that are adjacent to each vertex. So we have to go through one by one each one of the vertex and list down all of their adjacent vertices. For B, the adjacent the vertices to B is also A, D, and then E. So as you can see, this graph is undirected. Okay, that means that in this kind of example, there is an edge between A and B. And since this has no direction, so we can then say that there is a two-way relationship between these two vertices. So there is a way from A to B and B to A. And as you can see, in the previous vertex, which is A, we also list down that its adjacent vertex is B. And also for B, we also list down the A as one of its adjacent vertices. Okay. For C, its only adjacent vertex is E. For D, its only adjacent vertex is A, B, and then E. For E, it's this is our initial vertex, and its adjacent vertices are C, B, and then D, or B, C, D. Okay. Now, we can also use an adjacency list to represent a directed na graph. So what is its difference from the previous example? In the previous example, the edges do not have any direction. So we are having an undirected na graph. And there is a two-way relationship between vertices that are connected by an edge. But in this case of the directed na graph, we use the term initial vertex and terminal vertices. Because, for example, if you have an initial vertex A, there is an edge that is coming out of it. And we can then say that A is the origin, and then B is the destination, or A is the origin and D is the destination. Okay, so A is the initial vertex and B and D are the terminal vertices. So since this is directed, we can clearly see that the path is only from A to B, but not B to D. Okay, so we can see here that from B, all the outgoing edges only go to E. Okay, so we list down E as its terminal vertex. And then for C, its terminal vertex is only E. For D, it only goes to B and nowhere else. And then for E, it only goes to D and nowhere else as well. Okay, and that's it. Very easy, very easy. And for this graph representation on the other hand, which is the adjacency matrices, so we have an adjacency matrix A sub G. So we have a graph G, and A is the adjacency matrix. So that's why it's A sub G. And equals to a matrix. So a matrix of element A sub ij of a graph G is the n by n, or wherein n is equal to the total number of vertices, or V, or the set V. Okay, it's a 0-1 matrix, meaning the matrix only contains either a 0 or a 1. Wherein if the element A sub ij, wherein I refers to the I and the J represent the adjacent vertices, vertices, sorry, I and j represent the vertices is equal to 1 if v sub I, vertices v sub I and then v sub j has an edge. Okay, and we then specify 0 otherwise. So to understand that better, let us have this example. So we have a graph here, and the vertices are A, B, C, and then D. So we said here that we have a matrix A sub G. So this is our graph G, and this is the adjacency matrix A sub G. And we said here that the elements are of A sub ij. So we then list down all the vertices. So A, B, C, and then D for I. So that is for the row. And then for the columns, we also list down all of the vertices, the same set of vertices. Okay. And we said here that we have this is already the matrix that we have, right? And it's a 0-1 matrix, meaning the elements of this matrix is only 0 and 1. So and the A sub ij, the ij represents the vertices. So we specify it as 1 if there is an edge between I and j. Okay, so in this example, let's say we have this cell. So this cell is represented by A sub AD. So I is equal to A and j is equal to D. Okay, so this means that if there is an edge between A and D, we set its value as 1 and 0 otherwise. Okay, and we also mentioned here that the graph G is the n by n size. So n is equal to the number of vertices. So in this case, we have 4 vertices. So we can then say that our matrix is also 4 by 4, as you can see here. Okay, let us try to figure out or fill out our matrix. So let us start with A. So A does not have any edge with itself. So we specify 0. And then there is an, does A have any edge between B? Yes. And then between C, also yes, so 1, but not with D, so 0. Now for B, B has only an edge with, or B is only adjacent with A and D. So we specify here A sub BA and A sub BD as 1, and the rest are 0. Okay, and then for C, C is only adjacent with A and D. So A sub CA is 1, A sub CD is also 1, and the rest are 0. And then for D, so D is only adjacent to B and then C. So we set here this cells as 1 and the rest are 0. Okay, so that's it. Now let's have another example. So we still have the same set of vertices, A, B, C, and then D, but the edges are different. Okay, so let us start with this example. So given this kind of, given the number of vertices, so we are expecting that our adjacency matrix is still 4 by 4. Okay, so let us start with A. So A is adjacent with B, with D, and then C. So we set A sub B, A sub C, and A sub D as 1 and 0 with itself. And then B is adjacent to A and then C only. So we set this as 1, and for B and then D, 0. For C, it's adjacent to A and B. So 1 and then 1 for A and B. And for C, D, it's 0. And for D, it's adjacent only to A. So we set this as A sub D, A is 1 and the rest are 0. Okay, now we can also extend the adjacency matrix to loops. Okay, so we have this previous example and we just added loops here. And we can see that there is a loop an edge that loops within B and then as well as D. So we can see here that we have specified that B to B is 1 and D to D is also 1. Okay, and we can further extend it to multiple na edges. So previously, we have only had one edge between A and B and one edge between A and D. But in this case, A and B and A and D both have two edges. So A and B, we specify that there are two edges. And then A and D, we have two edges. B and A, so that is also 2. And D and A, that is also 2. Okay? That's it. Very easy. So now, let us try to see if we use incidence matrices instead. So we can also apply directed graphs here. Okay, so same idea. So if this is directed, let's say if this is directed, if there is only one way from A to B, so we specify here A and then B as 1, but not B to A. Okay, so let me show you with an example. Assuming that this is directed. Okay, so let us assume, just delete this. So let us do it one by one so you will understand what I mean. Okay, so let me just change this. Its format to there. Okay, so it is now a directed graph. So how are we supposed to do this? So we can start with A. So in A, there is no edge with itself, and there is a way from A to B and then A to C. So A to B and then A to C. And then for A to D, there is also a way from A to B. Okay, now if we are in B, so B does not have a way from B to A, and B is only going to C. So we only set 1, B and C, so 1, and for the rest it will be 0. Okay, and if we are in C, so C does not have an outgoing edge. So we set it all as 0. Okay, and then for D, there is no way or there is no outgoing edge from D, so we set this as 0 instead. Okay, so that's how we can use adjacency matrix when using when applied to a directed na graph. Okay, so let us review what we did. So A is only connected to B, C, and D. So this is correct. And then B has an outgoing edge or adjacent to C only. Okay, and then the rest will be zeros. C is not adjacent to from any other vertices, so we set it as 0. So as you can see, there are no outgoing edge from C, and then for D also 0. Okay, now let us have the incidence matrices. So for the incidence matrices, so this is the definition. So let G, consisting of a set of vertices and a set of edges, be an undirected na graph with V containing all of the vertices V sub 1 to V sub n, and the set E containing all of the edges E sub 1 to E sub m. So we can then say that the total number of vertices is n, and the total number of edges that we have is m. Okay, so then the incidence na matrix with respect to this ordering of vertices and edges is the n by m na matrix. Note that n refers to the number of vertices and M refers to the number of edges. N by M matrix, M equals M sub ij. So the elements are M sub ij. So the I again represent all the rows and J represent all the columns. Wherein the element M sub ij or M sub row col is equal to 1 if a certain edge J is incident with vertex I and 0 otherwise. So let us have that this example. So assuming that we have a set of vertices A, B, C, and D, so that means that V will be containing vertices A, B, C, and then D. And the N will be the cardinality of V or the number of vertices. So that would be 4. And then the edges, the set of all edges will be E sub 1, E2, E3, E4, E5, and then E6. So M here refers to the number of edges. So M is equal to 6. So we can then say that the incidence matrix with respect to this ordering of V and E is N by M. So we will have a 4 by 6 na matrix. M sub G, the incidence matrix M of graph G. Okay, wherein 4 refers to the rows and then the 6 refers to the edges. So as you can see here, we list down all of the vertices that we have in the rows and in the column. In the column, we list down all of the edges that we have also. E sub 1, E2, E3, and then until E6. Okay? So we said here that we have this matrix M, right? And each na element is represented by M sub ij. So in this cell, that would be M sub A edge 1. For this cell, this would be M sub B edge 2. Okay? So let's say we are in the cell. We are in the cell. So this would be M sub A, vertex A, and edge 5. So if A is incident, or if this edge 5 is incident with this vertex A, so we then say that M sub A edge 5 is equal to 1. Otherwise, we set it as 0. So same with the adjacency matrix, our incidence matrix is also a 0, 1 matrix that contains only zeros and 1. Okay, so let's have an example. So A here is incident with edges E1, E2, and then E4. So we set here A and intersection here of A and E1 as 1, A and E2 as 1, and A and E4 as 1, and the rest will be zeros. Since as you can see, A is not incident with E3, E5, and then E6. So let's look at the B. So B is incident with E1, E3, and then E5. So we set E1, E3, and then E5 with respect to B as 1. Okay, and the rest are zeros. For C is also incident to A and B. So we have, C is incident with A and B. C is adjacent with A and B, and is incident with edges E2 and then E3. So as you can see, we set this as 1, and the rest are zeros. So for D, D is incident with edges E4 and then E6. So we set E4 and then E6 as 1 for D. Okay, so yeah, that's it.